Hi, my name is Jack Walton, and this is my lab report on the Physics 21-2212 Lab 3 magnetic field of a bar magnet. The purpose of this lab was to understand the relationship between the distance and the magnitude of a magnetic field, to compare the measurements to the distance dependence predicted by the on and off axis equations derived from the PHYS law, and to learn how to visualize magnetic fields. The main physics principles used in this lab were the formula for magnetic field derived by Biot-Savart's law and the distance dependence equation of a magnetic field, shown below. In this lab, I found that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. The magnetic dipole of the bar magnet was determined to be 3.571 ampere meters squared, and the n value was determined to be negative 2.7313 meters.
Wow.
Some assumptions we made in this lab were that the z-axis points out of the screen, the y-axis points along the height of my phone, the x-axis points along the width of my phone, and the magnitude of the magnetic field is proportional to a constant multiplied by a power of a distance r. Some determined initial conditions in this lab include that the initial orientation of my phone to find the magnetic field and the Earth's magnetic field, the system is equal to the magnetometer and the magnet, the surroundings equals Earth's magnetic field. To conduct this lab, I used the magnetometer app where I determine the magnetic north by rotating my phone until the x component is close to 0. Then I align the stick along the bottom of my phone so that it ran east to west and orthogonal to the magnetic north with the magnet at the end. I located the magnetometer sensor on my phone by using tape which found the position of where x and y components were at their max and min. I then found the distance from the magnet to the sensor that produced a magnetic field with an x component of magnitudes 20, 70, 120, 170, and 220 microteslas. Lastly, I found the distance d perpendicular, where the net magnetic field had a distance of 100 microteslas. Here we have our data. On the top left, we have the distances and magnetic field values for each r value, and then there is the data for determining the off-axis field, and in the graph is our data between the magnetic field in the x direction and r, and to linearize this data we took the natural log of both values. And then determining the answers, we use the distance dependence equation to find the line of best fit, which was the slope, which was negative 2.73 meters, and we found to be roughly negative 3, which is what it was supposed to be. Then we found the magnetic dipole moment, starting with natural log of k, which is negative 14.152, or k being e to the negative 14.15, or which is also equal to 7.1427 times 10 to the negative 7th. And according to Biot-Savart's law, mu is equal to 3.571 amperes meters squared. Let's move on to the glow strip model. First, I created a cylinder to represent the bar magnet, and then I created a magnetic field around this bar magnet as a dipole. Then I determined the observation locations, the 2 on-axis and the 4 perpendicular locations. Then below that, I created the arrows at the on-axis observation locations for the magnetic fields, as well as on the right, the 4 perpendicular observation locations and their respective arrows representing the magnetic field. And then below that, I created an observation location that would be 45 degrees off of the axis, and below that at the bottom, I created the arrows which will represent the magnetic field at that location. And here we have the results of the glow strip model showing the different magnetic fields at each observation location and at the 45-degree observation location, and comparing the experimental magnetic field to the computational magnetic field. And to answer some concluding questions, what if in the experiment you oriented your setup so as to compensate for magnetic north? What if you hadn't done that and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would the results have changed? My results would have significant error, as the Earth's magnetic field will skew my measurements of the magnetic field created by the magnet, and therefore all calculated values will be less accurate. And imagine you had 2 identical magnets. What if you redid the experiment, but instead of using a single magnet, you used the two identical magnets stuck together end to end. How would you expect your measurements to differ? The direction of the magnetic fields would be the same, but double in magnitude because the two magnets would mimic a single larger magnet. And a few sources of error that can be deduced are human error due to measurement with a meter stick, other magnetic fields interfering, and accidentally bumping into the phone.